So I'm just going to show the video here again of our probe optical window with crude oil put on the window to replicate a high oil and water scenario, and then I'll activate the ultrasonics. Again, there's loud noise in this, so turn your headset down. And there we go. You can see how effective the ultrasonic cleaning really is. So the next stage of our research and development with ultrasonic cleaning has been to optimize the use of ultrasonics in high pressure applications up to 35 bar. And to understand how ultrasonics works, it works by producing microbubbles in water, also known as cavitation. These bubbles subsequently implode and provide the intense turbulence that leads to effective cleaning. And at low pressures of less than 5 bar, this can be achieved quite readily, but the action of the water pressure, when you start going above 10 bar, severely limits the ability for cavitation to occur above that threshold of 10 bar. So our research has focused on achieving the required ultrasonic power in the correct location of the probe, which is right at the window, that can deliver cavitation at 35 bar. So really many parameters affect the resonance of a transducer. That can be the material of construction, the length, the width, the shape, just so many things. And so to manually calculate a simple rod transducer is very straightforward. However, designing a transducer to operate efficiently at the right frequency, reducing displacement energy to facilitate a hold point, i.e. a flange, and then amplify that energy to maximize displacement energy at the desired location, which is at the window, is almost impossible. And so historically what's been done here is basically trial and error, and trying one type of transducer, seeing how it works. And it's worked to a certain extent, but it's not been proven to work in high pressure applications. So the software that we have been using to effectively design and simulate this desired transducer has saved us months and years of build and test time, and it's allowed us to produce a transducer that is ultra efficient and very effective. Like for example, historically 300 to 500 watts of energy has been used in this type of cleaning technique in low pressure applications, mainly to overcome the inefficiencies in the design. However, the software has allowed us to produce a super efficient transducer, and cavitation energy can be as low as 10 watts. So that's a step change in efficiency right there. But more importantly, for the high pressure applications, it's allowed us to, the increased energy efficiency has translated into cavitation at higher pressures. Typically, the high pressure transducer operates at 125 watts, which is still a fraction of the earlier design techniques. And you can see here this screen capture of the transducer simulation, and that's how we model the ultrasonics to be optimized at the end of the transducer right here. So this software has allowed us to develop and manufacture a transducer that's highly efficient, uses less power, and can produce cavitation at 35 bar. And as much as we'd like to trust the software completely, We still had a bit of trial and error to make sure that not that the transducer wasn't working correctly, but our system was communicating correctly with the transducer. So that involved a bit of testing, and you can see on the picture on the left here, we have the transducer. We placed it into a glass of water to just start testing the settings. And I'm going to press play on a video here. Again, just watch your headsets for the noise. So you can see we're just testing different settings here, making sure that the transducer is responding properly. So we did this until we were happy that the transducer could then go into an actual probe. And this video in the middle here shows the electrical components of the probe. And here's the probe that extends down through this tube into this pipe here. We've put this window in the pipe so that we can see into the pipe. Here's a pump jack to pressurize it up to 35 bar. And I'm going to play this last video here. And just so you know what you're looking at, this is looking through the window. This is the end of the probe right here. And we've coated the optical window with some crude oil. And the ultrasonics will kick in and you'll see the crude oil being cleaned and ejected from the window. So I'll just press play. This video is not so loud, so it should be okay. There you can see straight away the crude oil has been ejected from the window. This is just the test setup that we're showing you with the flange connections, the electronics, the pump jack to get it up to 35 bar. And there's the pressure gauge at 35 bar.